Because I think instead of just saying oh sorry the deadline is today and we're gonna just not give anyone any more points after today, that kind of defeats the whole purpose of this being a homework assignment that people can actually spend the time to try to understand the concept and actually do it. So I wanted to extend the deadline and so that you guys have a little bit more time to work on this. This is not easy programming because it has both the programming part, the details and whatnot, and also the concept part. We have not really dealt with anything like select from your other classes. Your other classes are mostly just a single program doing its own thing. There's no interaction with anything else. But in this class, because it's systems programming, so we have to be able to handle all that stuff. Hey, how was the trade show?
It was good.
I can see you got your.
That's some cool stuff I want to show you guys.
You want to do a show and tell?
Yeah.
All right. You want to do it yet now? I mean, you can either take a break. Okay. So remind me, when we are running, a little short of time. Okay. Jonathan went to the embedded system conference in Silicon Valley, and what they do is they just have a lot of vendors and manufacturers who basically have something to do with embedded systems. You have hardware vendors. All Atmel should be there. ARM should be there. And there will be software companies. Microsoft, are they still going?
Yep.
Yeah, Microsoft has their Windows embedded system version of Windows. At one point, it's called WinCE, Windows CE, and people just call it Wins.
Actually, I just think I didn't think. Never mind. Microsoft, I don't think was there. At least I didn't see it.
Not anymore.
Yeah.
They used to have a strong presence in embedded system shows because they want to get into the embedded system market. Can anyone imagine why Microsoft would want to get into the embedded system market?
Money. Yeah, money.
That's a lot of money because if you think about desktops, there's a lot of money. Oh, just look at our class here. We have a few desktops in the class, but what about embedded system devices? There's a huge number of embedded system devices. Your typical car, even if it's an EconoBox, typically has 10 to 14 processors on it. So if all of those processors are running Windows or one variant or another of Microsoft product, and they all have to be licensed, Microsoft can make a lot of money out of it. Okay. But there are software companies, at the show. I think there are development tool companies,
yeah.
Companies that make compilers and cross development environments, hardware debugging tools,
yeah.
Like ICE. ICE stands for in-circuit emulator. There will be companies making connectors. Even company making connectors will show up, at these shows.
I got a little demo pack.
Yeah. Well, that's because when you are developing embedded systems, unlike a PC, a lot of times you have to deal with prototypes. With PC, if you're a software person, you don't have to deal with the PCB itself. By the time it gets to you, you're just doing the programming, and it's pretty just hands off. You don't have to deal with the actual components. But when you're doing embedded systems, a lot of times, many things are programmable on an embedded system device, including some of the logic can also be programmed. And a lot of times, the chips have to be desoldered in order to be reprogrammed, and then you have to put it back on, which is a big hassle because these are all surface mount, tiny little parts. So what people do is they make special adapters. You solder the adapter onto the PCB, but then when you want to test your chip, you put the chip into the test adapter, and then it clamps shut. So it's a quick release kind of thing. You don't have to solder anything. Your chip is not soldered. The socket itself is soldered. So when you're testing it and you say, okay, I need to pull the chip out and reprogram it, you just have to unlatch the cover, pull the chip out, put it back into the programmer, reprogram it, put it back in, and you're in business again. So instead of having to go through the whole thing of, okay, let's put it through the hot plate and then use a hot air tool to desolder it, you don't have to do any of that. So it's really interesting. It's particularly related to this class, because this is a systems programming class, and embedded system programming is particularly interesting because the range of programming in that case can go all the way down here and all the way up there. Small embedded systems can run on a 50-cent MCU or microcontroller unit, in which you have 512 instructions and 32 registers. That's it. Okay, the device itself has 8 pins. You use up 1 pin for power, you use up 1 pin for ground so that you can apply power to the chip. The other 6 pins are programmable. So you can use the other 6 pins to control something on and off. You can use it to sense voltages from an input device and so on and so forth. And it will cost you about 50 cents if you order those things in large quantities. But then your programming becomes more difficult because you only have 512 instructions and 32 1-byte registers. We're not talking about 32-bit registers. We're talking about 1-byte registers. But you can still make use of those chips for many applications. It's just a matter of how well can you write a program and utilize the resources on the chip like that. But then the opposite end of that, which is a tiny little device, you have to program everything in assembly. It would be like big, huge systems, multi-processor, multi-computer systems, but they're still considered embedded because they're actually deployed in other devices. They're not desktop computers. So what did you see on the show?
I just thought it was cool because I don't know a lot about the embedded
aspect of programming.
So it was just kind of cool. I mostly just went around and asked people like, well, how did you get to where you are? And I'm a student. What can you tell me about what you're doing?
That is also a very interesting question because there's no easy path. There's no set path because because colleges and universities do not have embedded system programming classes. They do not have it as a focus either. So you can't really get a degree in computer science with an emphasis on embedded system development. They'll give you a general degree, you know about operating systems, you're good enough. Everything else you have to learn on your job.
Yep.
There's not a lot of good web resources either.
But with web resources, there's actually quite a bit. I mean, there's a lot of, it depends on your chipset.
Yeah.
And depends on your application. If your chipset is a popular one, like the Atmel, chipsets, I think there's a website called avrfreaks.net. Okay, so for those of you who are kind of, who wants to look into something like this, some people look up a website just because it has freaks in it. So. Okay, so this is the website called avrfreaks.net, and what it is it's not for profit. The website is completely run by non-profit people. They do have ads, I guess, to support the website and whatnot, and it's basically just a big, huge forum and a place to share resources for people who want to use the AVR, which is a family of MCUs for the application. So people talk about hardware stuff, software stuff, development tools. They talk about debugging techniques, debugging tools, and so on and so forth. It's a very big community, and this is a really, really good resource if someone wants to get into embedded system programming.
What are they representing graphically there to the right of AVR Freaks? There's like some little wires or chains hanging off.
Here?
No, up on just to the right of AVR Freaks.
Here?
Yeah, but what is that supposed to be? I mean, does that have something to do with embedded systems programming?
I do not know.
Oh, okay. If you don't know, then it must not be.
I do not know. But if also for people who want to get into embedded system programming, Arduino, is a it's kind of like an embedded system, on a single PCB. I believe you can buy components for the Arduino, series of controllers. You can get LCDs, you can get keypads, you can get motor controllers, you can get sensors and whatnot, attached to an Arduino, circuit board. So you can actually write programs to interpret the input from, let's say, motion sensors. You can also use the output of a board like this to control, let's say, RC servo motors. So now you can have a robot thing that can respond to motion, sight, sound, and whatnot.
That's cool.
Yeah, it is very cool. It is very, very cool. And what they have here is a simulator for the Arduino, which means for people who do not want to spend the money, or just want to get some idea of what it is about before they commit even more time and more money into it, you can run the whole thing as in simulation. Well, we already use simulation a lot in this class. Your virtual machine is a simulator. It's an emulator, but it's similar in terms of concepts. A simulator is also simulating hardware. So it's also simulating the interface to hardware components. So it's a really good resource, and the best thing about the AVR line is the GCC toolchain, the entire GNU toolchain is available for the AVR family processors. In other words, you can use GCC to compile your program. You can use GDB to debug your program. How do you debug a program that is running on an embedded system? Remember, an embedded system can be something that looks like this. It can be the flash unit of your camera. It can be, just about anything. So how do you debug a program that is running on something like this, and you are using a computer like this?
Two flashes. Two flashes mean this.
Well,
What you do is, in the good old days, that's what we do. We use LEDs for debugging purposes.
emulator? Can you write an emulator?
Well, you don't even have to do that. What you do is, you design the device with a particular type of header. Okay, basically like either a 10-pin header or 6-pin header, depending on the device. So that 10-pin header will allow you to connect the device to a dongle. I don't have one to emulate it, but you can connect it to a dongle, and the dongle talks to your PC through USB. So now there's a way for your computer, your desktop computer or your laptop, to talk through the dongle to the processor that is running in the device itself. And depending on the chip, some of the AVR chips support on-chip debugging. So GDB, you can run GDB on your desktop, but when you run your program, it's actually running on the device itself. And you have the full flexibility to set breakpoints, Control-C to stop the program, examine variables, and so on and so forth, while the program is running here. And the cost used to be very expensive. If you go to the show, you can see the full-fledged ICE in-circuit emulators. Those things run in thousands of dollars. But the devices that rely on JTAG, on the chip itself, those are in hundreds, or even less. Okay, if you get the older version, they're in the range of $50 to $70. So we are talking about the same tool chain that we have been using in this class. GDB, GCC, Make, and so on. But your program is actually running on a device that can be anything. I was trying to get a computer science club going, and one of the projects that we were trying to do was a light pen, in conjunction with a Wiimote, so that we can use Wiimotes for interactive whiteboards. And part of the thing was the programming. The programming on the light pen itself, it can be important. But the club is not going, and the project is has basically died. So there's nothing I can show you, with respect to that.
Real quick while we're on it, they had I learned about evaluation boards, or I never had known about those. So, and several like ARM offers one. And,
Yep.
There's different companies offering one, but we found a place that was actually giving them away. So,
This is the Butterfly.
So yeah.
Yeah, the Butterfly board is also based on the AVR chipset, and it has built into it. Does it have an LCD built into it?
This one doesn't. No.
Okay, but it has some pins, so you can actually connect components out out of it.
Yep.
Yep. Very good.
It was cool.
Yep. So we'll spend some more time to talk about that at the end of today's class. But for now, I'll just go ahead and remind you that the deadline of the homework assignment is reset to after spring break. So the Monday after spring break, the deadline is extended over there. But people who turn in on time, before today, will get the extra credit.
Do you mean by 10:30?
10:30.
Oh.
10:30 Pacific Daylight Saving Time. Yep.
So I got a question. Did you get my email about whether? I guess it doesn't matter, but if the maybe it does. People are still doing it. But for the broadcasting, the server broadcasting back talks about to itself. And is that the server is printing out messages, or
no? The server does not print anything.
Okay.
The server does not have input, it does not have output, it only talks through the sockets to the clients.
Okay.
Yep. Is that, yep, go ahead.
Are we going to get marked down as far as does have input and output?
No, it won't be marked down because my script will still run correctly, because I'm not even paying attention to what the server is printing out. If your server requires interaction to work properly with the clients, yes, it will be marked down. But if all it's doing is just spewing out stuff, to reflect its own state, or if I type something, it does something different, then it's okay because I'm not going to interact with the server through standard in or standard out.
So basically, if you're on the client that's sending the signal or sending, to the server, when you send, you should also get the message back on that client, correct?
Yes, the client who's originating a message should get an echo of the same message.
Because I kind of sent you two different ones so I could get in by the due date, but I didn't know which way that was, so I got one way and one the other.
No, the echoing is going back to the client who originates the message. Yep. All right. Any other questions about the homework assignment? Okay, maybe we can spend some time to talk about for people who have not, how many people did finish it and turn it in on time? So I would say that's about maybe half the class or so. So for the rest of the class, I would like to spend just a little bit of time so that we don't really delay the class too much. But I would like to spend a little bit of time to talk about how to structure your program. And we'll start with our notes on Monday. So we'll go back to our notes on Monday, which is 0326. And I wrote a text file on that day that talks about the overall code of the server as well as the client. Okay, so the client side, is actually quite messy because you have, all these special cases. Remember, I drew a picture, of the 4 endpoints of a client. You basically have to be prepared to select on any of those 2 of the 4. Well, I shouldn't say any of the 2. For each side of communication, you will have to, be able to wait on either the read or the write. Okay, so do you guys understand what I'm saying? Okay, let me just draw the picture again. This is a client. The client talks to the outside world using 2 particular files. Okay, I should say 3 files, but it's conceptually there are 2. Or you can look at it as 4. Okay. So on one side you have the socket. The socket is only going to use up 1 file descriptor, but it has 2 ends because it has 1 end for reading and 1 end for writing. The other end is, you have standard out and then you have standard in. And these 2 they have different file descriptors, but conceptually they are basically the same thing. It's just for interaction purposes. So what you need to do is make sure that you're not blocking the program unnecessarily. In other words, with standard in and standard out, you should only be blocking on one of them. With socket, excuse me, I take it back. Okay, standard in goes out like this. Socket in goes out like this. So for each path, you have to either block at this point or you block at this point. For this path, you either block at this point or you block at this point. Is that okay? So you kind of have to keep track of the state of your client program to remember so that you can set up the select call correctly. Any questions about this part? No questions? Now, the next question is, can you test your client before you even use your client to interact with your server? Because I think it would be a good idea to test your logic first to make sure your client is working correctly before you use your client program to talk to the server program. Because once you have interaction between the client program and the server program, and somehow the interaction is not correct, then you have a bigger problem because you don't know which end is responsible for that problem. It can be both. It can be one end or the other end, but it makes it very difficult to pinpoint which end is the problem. So what I'll do today is I'll just go ahead and write a simple program to do something like this, but not exactly the same. Okay? Any questions at this point? Yep.
When I first programmed this, I basically set it up so when I was anytime I was writing, I wasn't doing a select call. I thought we didn't have to do that. But so when I implemented doing the select calls, I set up the server to use select, and I was trying it out with the client. I didn't think it would make a big deal, but it kept on hanging up.
Potentially yes, because if you're writing without blocking, if standard out is blocked, in other words, if I type Control S, so that standard out cannot be written to anymore, that write call is going to block. But that write call being blocking means that you won't be reading from standard in either, because it doesn't get to that part of the program. So even if this path here is not clogged up, your program will still be blocking because that part is blocked.
Yeah, it didn't seem to block up.
It's not a
really
major.
pumping
It's not a major point deduction, but it is a very important point in terms of concept, because in our program, because we are only going to interact it mostly by hand, it doesn't really matter whether that much whether you're blocking it or not, because we cannot type that fast. The echoing from the server cannot come in that fast to the point where it's going to block standard out. And also, even if it does block on standard out, your typing is not going to be so fast that you will realize that your standard in is actually blocked.
Yeah, that was when I was basically copy and paste really fast.
Yep.
It was doing it, but once I implemented the block or the select call on the client side, then the problem went away.
Yep. Okay, so what I'll do is I'll just go ahead and write a very simple program to reflect what a client has to do. But instead of talking through sockets, we can use named pipes instead. So that makes the program a little bit easier to write, and also I don't have to deal with sockets, which is what your program has to do. We'll go to today's folder instead for this demonstration. Oh, okay, I'm missing one more dot. And we'll just say this is bidirectional pipe. Bidirectional pump, how about that? Okay. So we know that we'll be using certain things, UNI STD for read and write. We'll be using select. Now, I cannot remember the header files for most of these things, but that's why we have man pages. So select has its own header files, and we'll just go ahead and copy and paste this portion.
You just need this select.
You just need to select out of
Oh.
this is select out of
Cis slash
this slash.
select.
Go. And then we'll write. I'm going to hard code in this program, so so I don't have to spend time to interpret the command line. Okay, so I'll say. And
Would you
pipe.
scoot your window just a tad to the left, because it's not all showing up on the screen?
Oh, I can change the.
Oh, it's not a big deal.
I can change the zooming.
Thank you.
There we go. Okay. So I have two file descriptors for the two pipes, one for coming in and one for going out. And just to make this program kind of really quick, I'm going to blindly open the files, and then we'll check for. We'll just have one big check for errors before proceeding. So the error message is not going to be very useful in this case. And of course, we have to find out how to use open. Open, give it a file name, and then you have to tell it what you're opening it for. Read only, write only. In pipe is going to be read only. And then just forgot what the macro was. O underscore B. O underscore read only. Out pipe will open as out pipe, and it's going to be write only. Are we
Looks
doing
like
okay so far?
You capitalized an I in outpipe.
Oh, okay. Thank you. All right. So now that we have these two pipes, open and all the 4 file descriptors ready, we are ready to, handle this program. So how would you structure the program like this? Because, we have to decide, which way we are going, for each direction, and then from that we have to decide, which, how we are going to set up the select call. But before we go any further, I kind of know that we need this stuff also. So I'll just go ahead and use fd set. And
Is that FD underscore set? Is that
FD underscore set.
fd underscore. Okay. FD underscore set. Set. Okay. So how would this logic go? Well, you have several options. One option is to use a state variable so that you know what you're doing with each side of the communication. That's one way to do it, and I think that's really the easier way to do it. Okay, so we'll go ahead and do it that way. So we'll say in, pipe to standard out, and that's a state. We can probably use one single state for everything by mapping the bits, but that's just going to be less intuitive. So this is pipe from standard in state. Okay. So to write some comments, this one is the state of the pump from pipe in pipe to standard out, and this one would be the state of the pump from standard in to out pipe. Okay. Yep.
Would you tell me conceptually what part is the pump? The whole program?
The whole program is the pump. It's basically similar to what your client program is doing, except your client is pumping from the socket to standard out, pumping from standard in to the socket. This program is pumping from the named pipes to standard out and pumping from standard in. Sorry, take it back. From the in pipe to standard out, and from out pipe to from in standard in to out pipe. Okay. But in terms of the concept, it's the same. Okay, very very similar.
I've got a question.
Yep.
I guess when you find an issue with our program, do you actually let us know? Because now I'm thinking mine's all fine and dandy, but I guess it depends on how quickly you grade us. Because if we're going to take this and move on to our timeout,
Well, the timeout one is going to have my implementation available. So if you want to use my version, that's good.
But if we think we're happy campers with what we've got, I mean, I guess it's kind of, it's kind of dangerous.
That's like the real world.
Yep.
Okay, I guess it's our choice, huh? We either move on with what we have. Or
I would just go ahead and move on, because, if you test the program for the most part and it's working, I don't think, you have to do any real structural stuff to fix the program so that it will work for the timeout program.
Yeah, it's just if we run it through the paces as well as we can,
Right.
but somehow your script finds a flaw, it would be nice to know, but I guess we're not gonna know, we're gonna have to just move along.
I have to grade it, by the description in the homework assignment. So for the most part, this part here, using select call for the client side, since my description for the homework assignment did not say very explicitly that it has to do it like that, let me just go ahead and read that part. The client side should do the following. Instead of just listening to the connection and echoing, it just says echo everything from standard in to the connection, echoes everything from the connection to standard out. When standard in closes, also close the connection and exit. So it doesn't really say anything about minimizing blocking. Okay, in other words, when you did it, the way you did, writing without blocking, it fits all the description already, so it's fine. Okay. However, in terms of making the program, if this were a real world program and it's not a a single person interacting with each client to test the program, then the program with a write that is not after a select can potentially be blocking unnecessarily. So the rest of the function of the program is going to be blocked unnecessarily. So what I'm doing here is to illustrate, what you can do in order to make the program flow as the best it can. But it's not required in your program. All right. So now we have the state variables allocated, and it's time to get into this program. And I'll also use a flag. Well, I don't need a flag anymore. What I do need are constants. So I'm going to define some constants, so that I can use that constant for the state of each pump. Okay. So I can say pump wait for the input. I will just define that as 1. Pump wait out is waiting for the output. I will name that as 2. I'll define pump dead is 3, which means the pump is gone. I mean that pump doesn't exist anymore for one reason or another. Okay. Given these are the 3 states that I'm defining for each pump, how should I be initializing these pipes? What is the first thing that you have to do for each pump? You're always waiting for the input first, because unless you have an input, there's nothing to echo out. So that also means, so the way I'm looking at this program right now is, it can definitely benefit from structures already. Now, why do you think I think this program can benefit from structures already? I haven't even got down to the code to deal with the pumping and the state and stuff like that. Why do you think I think structures will be helpful in this case? Yep.
We've got 3 different types of variables that all relate to those 2 concepts, the in and the out.
Do you think the logic of the pumps is different? They are the same. Okay, so I can see that I can use a structure to help myself organize the program already. So I'm writing this program, pretty much on the fly. I mean, I did not have this program, prepared, prior to the class. I'm writing this program only because, in the discussion in the lab, some people brought up, certain questions, and I just want to illustrate, how to deal with, issues like that. So from this point, at this point, I recognize that this program is going to have some copy and paste if I continue to do it this way. So instead of copying and pasting, I'll just have a structure to represent a pump. So I'm going to have a struct pump here. And in the struct pump, I will need 2 file descriptors. One file descriptor for the input. I will have 1 file descriptor for the output of a pump. I'm going to have 1 character as my only buffer for that pump. So I read from the input file descriptor into the buffer. I output from that to the output file descriptor. Okay. And the pump also has its own state. So I'll just make it an integer in this case. So this means when I'm dealing with in pipe FD and out pipe FD, I don't need those variables anymore. And I'm just going to use the structures directly. So I will have to say struct pump. In this case, I'll have 1 from standard out pipe to standard out to standard out. And then the second one is pipe from standard in, like so. And then these 2 states are no longer needed because they're all included in the structures already. So when I initialize, I don't want to initialize those individually. I will write a subroutine to do the initialization. So I will just say void pump init. Now whether you want to put the name of the struct first or the action first, that part is kind of up to you. It's kind of subjective. I always use the name of the struct first so that I can tell what the subroutine is doing, what type of structure it is dealing with. I'm doing object-oriented programming in C. That's basically what I'm doing. So we have struct pump p pump pointer to a pump structure. And the only thing I really have to do in this case is say the P pump points to state, gets pump weight in, because that's the initial state of a pump. Now I can also make this a little bit more, with more initialization parameters. So I can basically specify the in FD and also the out FD. So the initialization routine would basically take care of those two also. So I have P pump in FD equals the in FD parameter, and P pump out FD equals out FD as the parameter. Are we doing okay so far with this subroutine? So when we have everything done here, then we can do the initialization down here. So we say pump init, the address of pump to standard out. The input to this particular pump is going to be in pipe. So in pipe FD goes here, and then the output is standard out, which has a file descriptor of 1. The next one is pump from standard in. And in this case, the input is file descriptor 0 for standard in, and then the output is out pipe file descriptor. Yeah. Are we doing okay so far? Now you can see that when I write the program, sometimes I would actually backtrack. I would write a certain part of the program, and then it suddenly clicks in my mind and go like, oh, I'm just recognizing things that are similar, and I will have to do some copying and pasting. So every time I recognize that, I stop and I restructure the program to utilize a subroutine and structure to make sure the program is is better structured, so that when I have a bug, inevitably I'm going to put some bugs into this program. But if I do it this way without copying and pasting, when I have a particular problem, the bug is only at one place instead of replicated multiple times throughout the program. So that makes the program easier to debug. Are we doing okay so far with this program? There's no error checking right now because I'm just writing the program as an illustration here. All right. So what am I going to do to stay in the loop? Well, I would say that I'm going to stay in this loop as long as pipe to, well, that's the other thing. I can also use a subroutine to do that. Okay. And pump is alive, and it takes construct pump. And what this subroutine is going to return is whether the pump is still alive. Okay. So for now, I'm just going to say that if the state of the pump is saying the pump is not dead, it's not equal to then this pump is still alive. Now, this is handy because now I can use this in my loop. I can say while pump is alive, the first pump, which is pipe to standard out, and pump is alive, pipe from standard in, do the following. Now, what if later on I decide, oh, I don't want to use the state member to tell me whether the pump is alive. Maybe I want to look at some other things. Guess what? It's no big deal to this part of the program anymore, because the logic to determine whether the pump is still alive is now abstracted into a subroutine. So if I want to change how I evaluate whether a pump is still alive, I can change that code instead of here. If I want to change the structure itself to represent a pump, it has no impact whatsoever here because it is now sheltered. It's shielded from that. Now, of course, I forgot to do certain things here because it is expecting a pointer to a pump, so I have to use the address of operator to do it like this. Are we doing okay so far with this? Okay. Next, what do I need to do? I need to determine the read set and the write set before the select statement, don't I? Right? Okay. So what I need now is another subroutine to do that. Pump is a prefix, and I would just say, pump set select, okay, or read write sets. Okay. Const struct pump p pump, and then this time I need two additional parameters. One is fd set read set. One is fd set write set. And because in C I cannot pass by reference, both of these will be pointers, because I'm going to change those particular sets. Okay. Are we doing okay so far? So this particular subroutine will look at a pump structure and then determine whether I need what I need to set in the two FD sets. So the way it's done is pretty easy. I just say, if p pump points to state is the same as pump wait in. Can someone tell me what to do here?
Yeah, you're gonna.
I need to do an FD set on which set?
Read.
And
Put
what would be the next number?
Put the file descriptor there, and then you do that.
Is it the file descriptor
Oh yeah, file
first?
descriptor.
descriptors first. Yeah.
I cannot remember which one goes first.
Yeah, I would.
File descriptor set. Yeah. File descriptor first. Okay, how do I specify the file descriptor? It's part of the structure. So in this case, it's ppump points to
File descriptor.
in file descriptor.
And you need the address of read set.
I do not, because it's already an address.
Sorry,
of.
you're right.
Yeah. I should have changed the parameter name to p read set to remind myself it is a pointer to a read set. Okay, what if p pump points to state is not pumped wait in? Well, technically it is better to make sure that it is the other one, right? Because it can be dead. So it is really better to do it like pump wait out. If you prefer, a switch statement can also be used in this case. But I'm just going to use this method here. Like so. Are we doing okay with this? Kind of? Yep.
Would it be okay to just set them both in the read and the write? Basically set them both, and then after you do the select statement, just see if they're both ready, and then do a read and a write. Then would that work?
Well, you can only be waiting on one or the other. Well, after you get it from the input, then you can wait on the output in the next round.
Oh, I mean, what I did was I basically I've got all four, so I just set all four in for read, or respectively for read and write, and then I just checked to see, well, if STD in and then the socket.
You can always wait on more. You always ask select to monitor more file descriptors than you actually need.
That'd be kind of wasteful, I guess. Though.
It's not wasteful. It's just that even if there's something, even if those particular file descriptors are ready, you're not going to do anything with it anyway. So from my perspective, you can do it that way, but from my perspective, I would like to only set the flags or only set the items that I'm really monitoring. But I guess that part is is optional. I mean, it depends on.
Yeah, I was wondering what maybe some of the advantages and disadvantages.
I don't think it has any disadvantages or advantages. Doing it either way. In this case, this looks more complicated the way I'm doing it right now, but I want to be very mindful of what am I actually waiting on at this point.
So does the select use up processor cycles while it's waiting?
No, it does not.
So the advantage to only having the things that you really need to deal with in your read set or write set would be that you're not just immediately coming back
Yeah.
from select on something that you're not
Yes,
gonna do
because
anything
if you
with.
wait on something, yeah, because if we do it the way you specified, where you specify every file descriptor I'm waiting, yeah, your select call is going to unblock every single time, because the useless end of this is always available. But then when you check whether you actually have something to read here, it was it's, well, you cannot read it yet. You have to use fd is set first, and then your fd is set is going to say no, what you're actually waiting for is still not available. And then your loop it becomes a polling loop, because when it goes back to the beginning, then you're going to wait on all 4 or 5 descriptors, and then your select will unblock again because, hey, this end is ready. Even though it doesn't do you any good, it tells you it is ready. And then your loop will find out that through the fd is set, it will say that, oh, I'm not ready yet. What I really need is not ready yet. Yeah. So it is better to block only on items that you really need to monitor. Right. So once we have pump, set, read, write sets, when we can then call those particular subroutines first. So we'll say pump. I can't remember my own subroutine name. By the way, you can also set bookmarks in VI. How many people know how to set bookmarks in VI?
That's sweet.
It's a M, lowercase m, and then you use lowercase a to z for local bookmark, and you use uppercase a to z for global bookmarks. Local bookmarks means if I use a bookmark here, okay, I'm just pressing M-A, on the keyboard, lowercase m, lowercase a. I can then go to elsewhere, in the program. If I use backtick, the symbol right under the tilde symbol, backtick A, it brings me back to this point. It's very handy. You only have 26 bookmarks per file. The more reason to partition your 5,000 programs into multiple source files. If you use uppercase, then you can actually cross files. In other words, if you're editing one file, you can actually use backtick and uppercase letter to go to a bookmark of another file. If I remember that correctly. I think I use that sometimes.
That was an int vim tutor. That was an int vim tutor. That's cool.
Not yet. All right, so we're going to use, we use the same thing here for both of these sets. So read set, write set, and this time I need the ampersand because these are all local variables. And then I can declare the local variables here, fd set, read set, write set. Make sure I clear everything first, so it's fd, and then I forget the name, CLR, because sometimes they use the abbreviation and sometimes they don't.
What does CLR do exactly?
It clears the entire set. In other words, it turns the whole set into an empty set, where none of the items is getting monitored.
Does it kind of do the same thing as 0, or?
Yeah, it's the same thing as assigning a 0 to an integer, but it applies the 0 to the entire structure in this case.
I thought you actually had to specify a file descriptor for FDCOR and it only cleared that one.
Sorry?
Yeah,
I thought FDCOR only cleared one file descriptor.
I think he's right.
I think 0 that sets them all. FD
Oh,
0.
that's
Yeah.
okay. That's not. That's only clearing
So,
one,
yeah, I
and
think
not
that
for
would
the
be a-
entire thing.
A syntax error.
Oh, 0. Never mind. I was right. You were right. So 0, turns the entire thing into an empty set. Thank you. You can see that I need my man pages to be on a separate page all the time. And that's how I write programs. I have a screen about the same size, but I run it at its native resolution, which is 6080 by 1200 or so. I cannot remember the exact number. And I have, when I write programs, I have about 9 X terms run, on the screen, one on man pages, one on, the command line, one on GDB, one on, editors, and so on and so forth. And they all have tiny little fonts too. I use very small fonts when I'm writing my own programs. But in the class, I have to use a larger font.
Why not just use a separate monitor for your man pages?
I don't like to turn my head, so I try to make everything so that they all stay within the range where I can just eyeball.
Dual monitors on Linux is a pain, I can tell you from a lot of experience.
Yeah, I don't like to turn my head, so I don't even want a bigger monitor, because you can get a 30-inch monitor of the same resolution. I prefer a 21 or 22-inch, because that's basically, the right view angle where I can just move my eyeball and not turn my head to go from one end to the other end. Talk about lazy.
Yeah, that's secret to the pros right there.
All right. So now we have both the sets ready for action, and so I'm ready for the select call. So we'll go ahead and do a select. I really should be using a number, assign it to a number, but I'm just going to do it this way, which is not exactly what I really should be doing. Okay, the select call returns a number that is useful, that is meaningful, but to us it's not that meaningful. But what I really need to do is to find out what is the number of file descriptors, or the max F file descriptor plus 1. And right now I don't really have a subroutine to do that. So it's time to write another subroutine to do that, right? So you say find max fd pipe from standard in. Oh, no, I don't need to do that. This one needs to find it from read set and just write set. And then we'll give it the address of read set, the address of write set, and a null because I'm not timing out. Okay, so now I go back and write my subroutine, find max fd.
How are you doing FDs from the read and write set? I just am interested to see how you get individual FDs from the read set and write set.
Oh, it's not that hard. Okay. Well, it depends on what is supported by, read set and write set. Question?
I thought you needed a secondary null for that. Yeah, because you needed the exception FD null.
Ah, okay. So it's one more null. Fortunately, the compiler would cut all of those things first. But it's okay. Here.
It's handy having a bunch of other people coding at the same time.
Sorry?
I say it's handy having a bunch of people coding at the same time.
Sometimes.
Not if one of them is me.
The rule of compiling no more than 10 lines at a time.
Say again?
Whatever happened to the rule of compiling no more than 10 lines at a time?
He's trying to show us what happens when you crash and burn.
Crash and burn. I used to go to programming contests.
That's awesome.
It's really a lot of fun, because you're really under a lot of pressure.
That's awesome.
Okay. So right here, it doesn't give me a way to detect, where's the last, what is the last item that I can actually access. Ah, there we go. Okay, a value of FD that is negative or that is equal to or larger than the FD set size will result in undefined behavior. So this is the upper bound already. I know what the upper bound is. FD set size. All right, so that's what we need. So what we need here is to scan through the whole thing, on both sets, and find the maximum along the way. So maximum FD starts with a 0, and then we'll say int I equals to 0. We say while I is less than max FD underscore, see, I cannot remember the name, set size. Do the following, plus I could have used a for loop, but it's just, for loop is a shorthand. Some people like it and some people do not like it. Since I don't teach that particular loop in cisp453, I just turn everything into a pre-checking loop, like this one. So we'll say if FD is set, okay, let's fix a few things first. Address of a pointer. Okay, there we go. So if FD is set, I, comma, read set, or FD is set, I, write set. Then I can say max FD is updated to I.
What was the FD underscore set size? You said that was the upper bound, but that's not going to be.
It's basically the largest possible file descriptor that you can use in a FD set.
Okay.
Yep.
But it's not necessarily set in our file descriptor set.
That is correct.
Got it.
Your program will only be using like up to maybe 8 or 9 or something.
Got it.
So this is way more than what you need.
Okay.
But as a general program, I need to make sure that I also test for those.
Sure.
So this is really wasting processing cycle. But
Yeah.
it's not but it does help make the program a little bit easier to deal with.
Right.
So then I would just go ahead and return max FD. I can either do the +1 here or I can do the +1 later. I'll do the +1 later because this subroutine is only responsible to find the maximum file descriptor. But when I actually make the call, then I will say it's the maximum file descriptor +1. Are we doing okay so far with this program? Yep.
At the beginning of the while loop, you declare read set and write set, but you've already declared it at the beginning of the program.
Yeah, so the local definition will mask the outer definition. So the outer definition, this one, these two will be masked by the other one. So that means it's not useful anymore. All right. So if I return from the select call, what am I going to do? Well, I have to find out, who has something to do and what to do, and and so on and so forth. So I'm going to do something like this. I will say pump tick. Give the pump a tick. Yep.
When you're going through a while loop and you go back out to check your condition, is that effectively going outside of the block?
Say again?
Is that when you go back to check your condition after you loop back?
Mm-hmm.
Is that basically like going outside the block? Is there garbage collection?
You mean at this point?
Yeah. Once you go back, you go.
At this point, it has
What I'm
all.
asking is,
Yeah, go ahead.
you declare FD, or you're declaring those sets, those FD sets,
Mm-hmm.
and then you go through and then you go back to check the condition statement. Are those then dropped or forgotten at that point?
Yeah, they are forgotten. That's why they have to be reinitialized.
That's effectively going outside of that block.
Correct. Yes. And read set. Write set. All right. So what I'm doing here is I'm giving each pump a tick. Now, what a tick is really just do whatever needs to be done, at this point. So we'll go ahead. I'm just copying the call so that it becomes the prototype.
Did you want to change one of those pump tick calls to have standard to have an in pipe as an argument?
Oh yeah. From standard in. Yep, definitely. All right. So now we have to define, what pump tick is going to do. So the first argument is going to be a struct pump, and it's going to be a pointer to a pump. and we'll have FD set as a pointer to, we'll have read set as a pointer to FD set, and also have write set as a pointer to an FD set as well. And now we can define what a single tick is. Well, what a single tick is depending on which state you're in, then you have different things to do. Okay, so the first thing I would do, this part is also programming style, but I would use a switch statement to figure out which state I'm in at this point. So I will say switch pump state, and then I define all the different states. The first state is pump wait in, and because I know C well enough, I always put the break right there. Okay, I don't even specify the rest of the program. I just specify the branches, put in the breaks, and because it does have a state called pump dead, I'm going to look for that too. If there's nothing to do, there's nothing to do, but I'm just going to put it there as well. Now I have a default here. If I were to write a program in real world, the default would have generated an error message because I should never get to that point. Okay? So that's why, that's what I usually do. When I write a program, I account for all the cases. I don't specify what to do with each case, but I specify all the branches first. Then I go back in and specify what I am supposed to do. And for the most part, with very few exceptions, you want a break between the cases. So I've always put in the breaks first so that I don't forget later. Okay, if I'm waiting for the input, what should I do? I have the reset here with me. So what I'm going to do is to check whether the file descriptor that I'm waiting on is there anything to do with the input that I'm waiting for. Is that making any sense? Okay. So if I write the code, you will see what I mean by that. So I'm going to say if FD is set, and I'm going to refer to my in file descriptor, and say that in the read set, is that set? If so, I got something to do. Is that making any sense? All right, so what I need to do here, I have to be careful because I have to say int read result here because I want to know what is read returning. It is important. So I will say read result equals to read, and the file descriptor is just pump in file descriptor. I'm reading in only 1 byte into my buffer. So we have p. I need the address of p pump. What is it? I think it's buffer. Yep. It is a single character. Then I have to see whether read result is 0, because if it is 0, then this pump is dead. There's nothing to read from anymore. Okay. Now you can declare the pump dead when there's nothing to read, or you can do some other thing. But in this particular program, I'm just saying that if the pump is dead, if there's nothing to read from the input of one pipe, this particular pump is dead. So I'm going to say p pump state is now pump dead, because the pump is no longer it no longer has an input anymore. I'm reading in a file in this case. Else, okay, because otherwise I have to do something. What I need to do else is what? First of all, my state is no longer waiting for the input. I just got the input, right? So what is my next state? I'm waiting to send that byte out, okay? And that's it. I don't have to do anything else. I just change the state, because the next time when I go back to pump set read write sets, it's going to look at the state of the pump, and it will pick the right file descriptor to set in the right set as well. Yep.
So, if going back to your picture here, your pump waiting in would be where the arrow enters the box, and your pump waiting out would be you're waiting
for standard out to have at least 1 byte available so I can write.
Okay, thank you.
So now that we have this one, pump wait out is going to be about the same. It's dangerous to copy and paste, but I'll do it here. 60 to this point, yank, paste. when you use copy and paste, you really should go after each and every single line and make sure that you make all the necessary changes. Now this one has a right result. I'm not really sure that we should be interpreting that, so we'll just go ahead and not do that. So it's definitely a bad programming approach here. Okay, so let's say I just wrote that one single byte out to the file descriptor of this particular pump. What should I do next?
Change the state.
Change the state. Very good. So p pump state is now updated to
Pump waiting in.
yep. Wait in again. Very good. Excellent. All right. So do you think this program is ready? Sort of. We'll give it a try. I just wrote about 107 lines, and now we're going to test it. All right. Well, this is how you get some excitement out of life.
Yeah.
Bi-directional pump, bi-directional pump. Let's see. And I'll just go ahead and turn on some warnings here. Now the -02 is not just for optimization. It forces the compiler to consider certain things like dead branches and whatnot that normally would not report problems, even with warn all. So in this case, we have several problems, and we have in-pipe file descriptor not defined. That's usually easy stuff to fix. It's mostly on line 82 and 92 and 99. Okay, 92. Oh, well, just do that. No? Constants. I think we need types or stats. Types, stat. Types or type? Types. Okay, got it right. Ah. Okay, open is not actually in it. Open is actually in file control. Okay, file CNTL. There we go. Yay. All right, so now we have to test the program. To test this program, we have to make two FIFOs, so they have to be in the same name too. And of course, I have already forgotten the name that I chose to use, in the hardwired part of the program. Really should make a breakpoint, label here. Oh, by the way, the bookmarks are persistent. If you if you set a bookmark in a file,
That's cool.
when you open the file again, the bookmark stays there. Otherwise, the bookmark is not very useful. All right, so I use in pipe and out pipe. Very good. Okay, so we say make FIFO. What was it again?
Lowercase n.
Oh, okay, but this time I set a bookmark. So in pipe, out pipe. Okay, make FIFO in pipe, make FIFO out pipe. All right, so we'll go ahead and run the program. By dir pump, and then we'll use two other terminals to help us with this program. Okay, we have in pipe, we have out pipe, so we'll go ahead and cat and pipe to, let's see, we want to pipe to in pipe because the in and out are from the perspective of the program itself. So when you're outside of the program, you have to kind of flip the perspective because the in pipe is actually going into the program. So from here, we want to cat to in pipe.
You do a redirect?
Yeah, redirect. So
I was stuck on you using the pipe symbol. Can you say that again about flipping the perspective?
Well, in pipe is this guy here.
Right.
So from the perspective of the program, it is an input, is you read from it.
Right.
That means from the perspective of someone interacting with the program, you're writing to that pipe.
Oh, okay.
Yep.
That makes sense.
So I need another terminal to cat from out pipe, because once again, out pipe is from the perspective of the pump program itself. So from outside of the program, I have to look at things from the opposite direction. All right. So the first thing I really need to do is to run the program and type something here. This is a test. It should be echoed to out pipe. So now I look at this program, it's getting it. Yay. So now I look at the other way, I say this is content coming in from in pipe. Press the enter key, and it's also getting it. So the pipe is working in both directions. It's pretty hard for me to test the blocking part, whether blocking one part will actually make it stop working. But I can try. So the way I do it is I can use Control S to just type Control S on the keyboard on one of the standard ins. So in this case, I'm doing Control S on this end here, and then I go back to this one because everything that I type here should be echoed on the other side. Okay, so I'll keep going, keep going. Actually, I don't know. It's hard to test because I can't. Once I type a Control S, I cannot type anything here to send back out to the other side. But as soon as I type Control Q, it releases. It unblocks everything. So everything that I type here will be released. Okay, I know what. I go to this part here. Yeah, I go to this part here. Okay, this part is taking the out pipe from my program to echo it on the screen. So if I type Control S at this point, it's going to block the output. I'm blocking, in other words, this outlet here. The other program on this side is saying, okay, I'm not taking your cars anymore. So you can still send cars on the highway, but at some point the highway is going to back all the way up to here. Okay, so now I can then test the program by just typing on this part here.
You copy and paste the screen.
And at the same time, I still have to test this part and make sure that this stuff is still echoed. So that's how you test it. I can copy and paste stuff, yes. Like that.
Yeah.
Oh, okay, I have to copy first and then paste. There we go. And the program should not be blocking. I mean, in other words, I can keep doing this indefinitely. Now, how do you know the program is still ticking? Remember, there's no output now because whatever I'm sending here is from standard in to this part here. This is blocked. I have just blocked this program, but I haven't blocked the other side. So if I write something here, this is new content should still be, should still be displayed at bi-direction pump. Press the enter key. That part is still working. So no matter how much stuff I'm sending from the program to its out pipe, this part should still be working because the block is only selective on that one. Is that okay? I mean, do you guys kind of get an idea of what I'm trying to do here and how I am testing the program to see whether it's working or not? Sort of. Okay. So, Jonathan, do you want to talk some more about the embedded system show?
Just that I didn't. I've worked with in the ET302 class. We were using like a kind of a learning board or
A parallax,
parallax
board. Basic stamp.
Basic stamp.
Yeah. The basic
So-
stamp, as the name implies, is quite basic.
Yeah.
Yeah.
So it was cool to see what the other, what else was available, and just what's available to just practice doing the embedded code and kind of what we're doing, just in a more basic kind of level. So excited to try that out.
It's very interesting because you don't have an operating system. In other words, if you want your embedded system board to talk to another device through a serial port or something like that, you cannot just say, oh, I want to open /dev/TTYS0, which is serial port 0 typically, or TTY USB S01 or something along that line. There's no driver.
Yeah.
You are it. You are the one who have to control the UART, universal asynchronous receiver transmitter. That's UART. So you have to program the chip and actually write the interrupt service handle routine, and you have to implement your own circular buffer, and you have to do the whole 9 yards. So from that perspective, you start with basically no tool. You have a C compiler, but there is no operating system, no such concept as files or pipes or sockets or anything along that line. You are interacting directly with the hardware devices. If you want to provide any type of high-level function, like networking or the FIFO concept or whatever that is high level, you have to do it. And also, in embedded system programming, one of the devices that we don't have to deal with, right, at least not for now, is called a timer. In embedded systems, the timer is an extremely useful device, because what it does is it gives you that periodic tick. Okay, every so often, you can program it to take, in milliseconds, in microseconds, or in, tens or hundreds of milliseconds. But once you program it, it will give you that regular tick, and you can use it to keep track of time. You can use it to do certain things that you have to do periodically, and you can also use it as the basis for your real-time kernel. You can implement a real-time kernel using that sort of thing. So it gives you a lot of flexibility that that we do not have when we play with Linux, because the system is already written. But
There's
then
quite a bit of support out there for people that are learning, and some of the different ARM with mbed. I think just mbed. They have like an online. It's like like a web page or like an online basically IDE, and they have different things that are code, like they share code and for their their development board, they have those there. They have all kinds of different code that you can look at, and people contribute. You can share code
and you can look at this device here. Just look at this device. It already has
M3.
It has USB serial port, has analog input, and it's running on a single chip. And this is also running on an ARM processor, a Cortex M0 device. It might have enough RAM to even run Linux.
Oh yeah.
So it depends on the process. Well, we can take a quick look here.
Okay.
8K RAM, 32K flash, not quite enough to run Linux. So in this case, you pretty much have to write. There's no operating system support. You have to write your own code to deal with all the devices.
Oh, but it has that thing you were talking about, the asynchronous receiver transmitter. So you were saying on some stuff you have to implement that yourself.
Well, the device you don't implement yourself. The hardware device is there already, but you have to control the device to make use of it. So you still have to write, fairly low-level code to make use of the devices. But it does have USB, the USB bus driver, and it has UART. and general purpose I/O. So and 6 channels of input, analog to digital converter. So this chip is, or this little board here, is actually quite capable. I mean, you can use it as the quote unquote brain, and connect additional circuit boards and additional devices to it, and make use of all of these peripherals. Yep. But for for bigger devices, if you get your device, and you can have about, I would say about 256 megabytes of RAM, you can start to run Linux. And there are single chip devices like that. And one example is, I know you guys have to go, it's called Raspberry Pi. Raspberry Pi. And let me see if I can find a picture of that. So I want to show you the picture. And that's it. When you look at this picture, I guess it doesn't show very well. This is the main processor, and that's it. All the other chips, I think this one, maybe just a additional peripheral chip for something else. But it doesn't have RAM, it doesn't have ROM as separate chips. I think they're all built into the single chip here. And this one can run Linux. The Raspberry Pi, runs Linux. And once you run Linux, all the other devices are very easy to deal with, because they all appear as files. Exactly. All right. Well, we are at the end of today's class. I'll see you guys on Monday after the break. So work on the program. Keep working on Socket 2, and then on Monday after the break, we'll talk about Socket 3. I will release the description of Socket 3, so for people who have finished Socket 2 already, they can get started earlier.